Something much bigger than a new electric car is starting to take shape. Beneath all the usual talk about range and speed, the real story lies where every journey begins, inside the battery. Lithium-ion took us through the first chapter of the electric age, but it also brought problems like fire risk, battery fade, and supply pressure. Tesla's 2026 aluminum-ion battery begins a whole new chapter. One built around true safety that silences the headlines and endurance that can outlast the car itself. The question is no longer about who builds the fastest sedan, but who earns the trust of families when the road turns hot, cold, long, or rough. If you want clear and deeply researched tech stories, help us keep going. Tap subscribe to push Westech beyond 223,587 subscribers and hit the notification bell so you never miss the next update. Now, let's open the pack, trace the heat, and see why this chemistry could truly mark the end of lithium-ion. How does Tesla's aluminum-ion battery remove the fire risk once and for all? We chose EVs for a cleaner future, for savings, and for smart technology. But with lithium batteries, the trade-off often feels too big. Our safety shouldn't come with the fear of sudden fire. Luckily, Tesla has an answer. They're designing a battery pack that doesn't contain the flammable liquid electrolyte found in lithium designs. Nothing to burn, nothing to ignite. The main ingredient here is pure aluminum, which brings an edge that graphite, silicon, or carbonate in lithium batteries could never offer. Stronger heat resistance. Lithium starts to face danger once it reaches 120 degrees C, but aluminum continues working perfectly between 200 and 250 degrees C. That's nearly double the thermal safety range. But there's a bigger breakthrough few are talking about yet. Tesla's aluminum cathode superstructure being tested since Q3 this year. Why is it so important? Instead of the flat closed cathode used in typical lithium batteries, the solid aluminum cathode is designed as a honeycomb lattice made of thousands of nanohexagons. This 3D honeycomb increases the surface area of the cathode about 5 times and spreads heat almost 40 times faster than lithium. Aluminum not only withstands high heat, but even cools itself. High temperatures are no longer a threat. This technology reaches complete safety with a nanoceramic coating just 0.5 micrometers thin, about 1/100th the thickness of a human hair. This layer smooths the cathode surface and helps aluminum ions move evenly, preventing energy congestion that turns into hidden hotspots or explosions. This structure also removes the battery industry's worst enemy, dendrites. Those tiny metal spikes that grow inside lithium cells and puncture separators simply don't form in aluminum cells. That means no complex cooling systems, no heavy shells. The battery itself becomes the safety barrier. Tesla is removing the danger at its root to protect drivers. The biggest benefit is peace of mind when driving an EV. The risk of fire drops by about 99.3%, even if the battery overheats or takes heavy impact. That's especially important for people driving through America's hottest areas, Arizona, Death Valley, or summer highways in Florida and Texas. Long trips become easier when you don't have to worry about a short circuit hidden inside the pack. Even after driving for 12 to 14 hours in 110–115 degree rough conditions, with road surface heat pushing near 90 degrees, the aluminum batteries won't pass 60 degrees C. That blocks every chance of swelling, sparking, or fire. In Tesla's internal crash tests, the fire risk in aluminum-ion batteries dropped to only 0.05%. That means just 1 in every 2,000 packs caught fire under extreme collision conditions, about 50 times safer than a typical lithium-ion battery, which has a 2.5% fire risk in similar crashes. In lithium designs, impact and friction can raise cell temperature to 100 degrees C, rupturing separators and releasing flammable liquids that ignite. In aluminum cells, temperatures only reach around 70–80 degrees C, still inside the safe zone. Even if they break open, there's no liquid fuel, no flame spread, and no chain reaction, where lithium dendrites would trigger explosions. Aluminum cells simply stay stable, warm slightly, and keep control. Can Tesla's aluminum-ion battery really erase all the dangers we've lived with for years? If you're waiting for this technology to bring full safety to your family and every long road trip, comment "zero fire risk" to let us know. Tesla also built protection at the pack level. Once the risk of combustion inside each cell is gone, the next challenge is making sure a single cell failure never grows into a full fire. This is where Tesla's aluminum-ion design separates itself. It's not only safer in theory, but engineered to fail safely. In real situations, which is what truly protects, lives on the road. Every small module inside the pack is wrapped in a thin aerospace-grade barrier that blocks heat transfer and channels vented gas through a dual exhaust spine. If one cell vents, microfuses open in just 4 to 6 milliseconds, cutting current before heat can spread. In stress tests following the SAJ2464 nail penetration method, peak temperature hit only 82 degrees C and dropped below 60 degrees C within 90 seconds, with no ignition nearby. Fast isolation and guided gas flow stop a chain reaction the moment it begins. The next defense layer suppresses heat spread at the pack level. In trials, Tesla deliberately pushed a cell to failure inside a module heated to 70 degrees. Because of the honeycomb aluminum cathode and ceramic surface, no nearby module passed 45 degrees C. Lithium packs depend on complex liquid cooling and armor to get close to this result. While the aluminum pack naturally acts as its own firewall, three-dimensional heat paths and non-flammable electrolytes make sure heat dies where it starts. Another important upgrade is controlled venting. Since aluminum-ion cells don't use carbonates, there's no built-up fuel gas ready to ignite. Tesla's vent system keeps peak gas flow under 8 liters per second and directs it downward through the floor. In safety tests, smoke and gas levels stayed far below those seen in lithium fires, and visibility inside stayed clear enough for people to escape. The air remained breathable long enough for evacuation. Tesla's crash detection reacts faster than the eye can blink. When sensors detect a major impact, the high-voltage circuit drops below 60 volts within about 10 milliseconds. Combined with arc-proof connectors and gel-sealed joints, it removes almost all post-crash sparks. In sled tests, the chance of a post-impact fire was around 0.030.006%, about 50 times safer than older lithium packs. Instant depowering and arc blocking remove ignition entirely. Everyday bumps and hits are also part of the plan. The strong tray shell spreads the impact of debris or curbs and reduces local strain by over half compared to flat trays. In underbody impact tests at 35 km/h, the inside temperature rose less than 12 degrees C and recovered automatically after isolation. That turns damage into maintenance, not news headlines, the kind of safety that truly matters daily. Now, about longevity. Most lithium batteries in today's EVs, like the Tesla Model 3 or Model Y, last about 300,000 to 500,000 miles before dropping to 80% capacity. After that, they lose half of their remaining capacity within another 100,000 miles. But Musk's aluminum battery completely changes this. We're not talking hundreds of thousands of miles anymore. It can last around 3 million miles. Basically, it can outlive the car and even its owner. Why does it last so long? Once again, aluminum fixes what lithium cannot. In lithium-ion batteries, the electrolyte breaks down a little after each charge cycle, leaving solid deposits on electrodes that block lithium movement and slowly kill capacity. Aluminum-ion batteries use a gel polymer electrolyte with a boiling point near 300 degrees that doesn't evaporate or form those solid layers. That means almost no loss of performance over time. There's also no issue with fast charging at high temperatures. Lithium batteries lose efficiency above 70 degrees C, but aluminum ions move freely and handle high current flow easily. That's why lithium packs can only fast charge at 35 C, while aluminum ion ones can handle 100 C, reaching 80% charge in about 3 minutes and full charge in under 5. That's quicker than refueling a gas car. Put simply, aluminum batteries can handle 20,000 charge cycles, about 3 million miles, and still keep 90% of their strength. The average American drives about 12,000 miles a year, meaning this battery could technically last 200 years. That's about 7 times the life of a Hyundai Ioniq. 5 battery used daily for 30 years and over 11 times the lifespan of a Chevrolet Bolt's 17-year battery. With safety and lifespan proven, the bigger picture comes into view. The lithium-ion era is ending, not just in theory but in fact. It starts with safety and expands to economics and infrastructure. Insurance reacts first, since aluminum-ion packs show 50 times fewer fire cases and almost no toxic smoke, cutting premiums by 14 to 22%. Fleet managers benefit too because fewer total loss fires mean lower costs. Shipping becomes easier as well. Lithium packs are treated as dangerous goods, but aluminum packs aren't, which cuts shipping costs and time by around $120, $180 per pack and up to $240 per kilogram for air transport. Lower logistics costs speeds up production and delivery. Building codes also adapt. Fire rules focus on flame spread, but if that spread doesn't exist, underground garages and charging stations need fewer barriers. Developers can save 6 to 11% in upfront construction costs, helping EV infrastructure grow faster. End-of-life recycling also leans in aluminum's favor. Over 97% of aluminum can be recovered through regular smelting compared to 70–85% for lithium routes, which often produce toxic waste. That makes aluminum-ion more